Okay, welcome. Today is 7.0. Oh, let me make a quick adjustment here. 7.08, continuous extensions. So what we're going to be doing here is we're going to be taking things that are maybe not continuous and fixing them, or just kind of forcing them to be continuous against their will, okay? Remember the types of discontinuities there are. There are jump discontinuities where the left and right limits aren't equal. There are removable discontinuities where maybe they do kind of meet at a certain point, but maybe that point is missing. And we have infinite discontinuities where we have vertical asymptotes, okay? So kind of keep those in mind today. That's gonna help us drive our ideas of continuous. We need to make sure the left and right are equal and that we had a value at that point. So in this case, what we have is we have a quadratic and a linear function. And we can see that we actually have two variables here. We have x, right? So to the left of 2, we have this kind of quadratic function. I don't know, it's some kind of quadratic. And then when we get to 2, it stops, right? And at 2, it stops when we go into this linear function, right? And now what we really need to know is what kind of value, what linear function itself, right, would actually match up to make this continuous, right? Because if we change the slope, right, that's actually going to kind of change the way that we define this function, right? So we want them to meet perfectly. And we're going to try to, find a value here for this function that'll make it actually work. So remember that we need these two things to be equal at that point. We need the left to be equal to the right-sided limit. So we need this left to be equal to the right. So step 1 is just making sure that the left and right are equal. Well, how do we do that? We can actually force them to be equal by setting up an equation. Now, we have set them up to be equal, which is a great first step, something that we're driving to do here. But now what? And your brain might be thinking, well, we have two variables, we have k and x. Well, we actually know what x is supposed to be at that point. So at that value in time, we're talking about 2. So let's actually plug that in. So think about 2, actually just like plug in x, which in this case is going to be 2 squared plus 2 times 2. Minus 15, and we still don't know what k is, so we'll just leave that as k. But we're going to put that as 2k. Notice how I just kind of switched that order there. Okay, because instead of putting k times 2, right, it's just 2k. And now we can actually do some math here. 4, we can evaluate this entire left side. There's no variable left over here on the left side, so 4 plus 4 minus 15. And over here, we can't evaluate all the way. There's nothing to simplify on the right side. But what we notice here is, like, if we continue to work on the left, 4 plus 4 is 8 minus 15 is negative 7, that we get something like really, really nice. We get something really, really nice because now we can actually get rid of those things. We get negative 8 and we can divide it by 2, right? And if we divide it by 2, we can actually solve for that value of k, which I kind of just started to just kind of see what would happen, and I eventually just kind of stumbled upon a great solution, find the value k that would make this continuous. I'm just going to kind of check my work here, just making sure that I did everything correctly. So I plugged in 2, everything looked good. 4 plus 4 is 8, yep. I just don't remember this answer from earlier before. And we got negative 4. Now we could do like a check here. And our check would be a kind of check for continuity. We'd have to make sure that the left is equal to the right. That is one definition of continuous. So I can actually plug this in and see. So our left-sided limit, so as we approach 2 from the left of this function f of x, what did we get? Let's see, let's plug in negative 4 in here. Well, there's no negative 4 to plug in, so we would just plug in 2's. And we already did that work, didn't we? That would give me negative 7. If I plugged in a positive 2 from the right direction, which we're still going to find, oops, this got to be f of x, not f of 2. From the right side, if we plugged in a 2, that would be, let's see, 2x, 2 times some k value, right? And that k value we said was negative 4, so that'd be negative 8 plus 1, which is also negative 7, right? So the left is equal to the right, but what is f of 2 itself, right? And f of 2, we would obviously use this one because 2 is equal to 2, right? Not greater than 2. It's including the 2 in this top function. So we would use this top function to define it itself at that exact moment. And of course, that's also negative 7. So since all of those things are negative 7, that basically means they meet at negative 7 and there's a point at negative 7. This just kind of is a proof that our new function is continuous, or our function with that value is continuous. Okay, so this is kind of fixing those continuities to make sure that we don't have a jump. So set them equal to each other, right? That's one condition for continuity. And once you have that, just make sure that everything is in fact the same. Okay, I'm gonna clear this one. Another type of problem would be create a formula such that the following function is continuous at x equals 3. Well, let me give you a function real quick. That function is gonna be f of x again. We'll just call it f of x. And we're gonna have a rational function. That's gonna be x squared plus 2x minus 15 over x squared minus 9. Now we actually want to make it continuous at x equals 3. Well, let's just see first of all, this is one of those things where it's hard for me to know what to do, but we are gonna see like what happens when it's continuous at x equals 3. So let's actually plug in 3. Let's actually find f of 3 and just see what happens. So we get 3, and that's gonna be 3 squared plus 2 times 3 minus 15 over 3 squared minus 9. We're going to get 9 plus 6 minus 15 equals, or over 9 minus 9. I get 15 minus 15, which is 0, and 9 minus 9, which is 0. Now, you have to remember, 0 over 0 is not 0. Type it into your calculator. It will not say 0 in return. It'll say error. It'll say can't divide by 0. And in fact, this is the indeterminate form. Right, in this indeterminate form, when we're evaluating rational functions like this, tells me that we have a hole here. This is an issue because we want to create a formula such that the following function is continuous. And if it has a hole, that's a removable discontinuity. So in a situation like this, we need to actually take that out. We need to find out it's a very similar function, and we need to find out how can we make that function continuous. So think about this right now. It's kind of cruising along. It has a hole, and then it continues going. What we want to do is we want to fill that in. So you actually want to find the location of this hole and say, hey, use this function, but at that point, here's the value that you're going to use. Here's the point that you're going to fill in. So we get to keep this function, but then add in the value that we need to patch it. We're kind of putting a patch over the top of it. So you may hear some noise behind me. I'm sorry. So let's actually find the location. Remember how we find the location of these holes? We actually factor them. So we got x squared plus 2x minus 15 over x squared minus 9. And then if we factor the top, let's see. I'm thinking of factors of 15. And I got 1 and 15, 3 and 5. That's it. 3 and 5 will give me 2. Okay, and since that's positive, we'll see the negative 1 has to be a negative, right? Because that's negative 15. But then they got to add up to a positive. So our greater absolute value for that plus that 5. On the bottom, this is a difference of perfect squares, x minus 3 and x plus 3. Okay, and now here's what actually happens, and I'm going to annotate this. This is our removable discontinuity right here. This is our removable discontinuity. Notice that if we were to plug in 3 here, right, for each one of those, that's where that 0 over 0 comes from. So we're actually going to factor that out. We're going to remove the removable discontinuity. And what we're left with is a very similar function. We can actually call it like it's, brother or sister g of x over here, x plus 5 over x plus 3, right? And now we can actually plug in that 3 into kind of its sister, because this is like the same function as the original, except it doesn't have a hole in it. It is actually defined at that value because we've gotten rid of that hole. So now if I plug in that 3, we get 8 over 6, which is 4/3. Now, this tells me the location of that hole, right? So we had a hole here, right? But now we actually know the location. That location is at 3 and then 4/3, right? So what that tells me is we have this brand new function, this new formula to define, this function, but making it continuous. Let's give it a brand new name, h of x. Now this brand new name, this brand new function is going to be the following. It's going to be the same function. It's going to act the way that function does all of the time, except one time. Right? There's one time where this function doesn't work and it gives us a hole. Remember that was at 3. So we can use this function whenever x is not equal to 3. but we want to use a different function. Remember, there's a hole there. So what's the value of that hole? We want to use the value 4/3 when we do have the x value of 3. So what was a hole, right, given this original function, we now can say, hey, once you get to that point, it's going to be 4/3. And what that does is that kind of patches that hole so that we have this beautiful continuous graph. And this piecewise function kind of defines it, right? First, our original function, but second, where to define that function when it arrives at that hole. Okay, so this is our formula. This is our brand new function. Notice how it's a piecewise function consisting, once again, of the original function plus the location of the hole to define it at that point. This is another example of a continuous extension. This is how I would patch a hole. This is now your opportunity to kind of go and try some of these on your own.